So, welcome to our continuing discussion on dimensional analysis. Dimensionless groups, dimensions and units is what I had covered in the previous two lectures. And today we will go on to dimensional analysis, that is, how do you use dimensional analysis to find out relations between quantities. So, I told you that there are two kinds of dimensions, fundamental and derived. By convention, fundamental dimensions are mass, length, time, temperature, current and light intensity. With their SI units, kilogram, meter, second, Kelvin, ampere and light intensity is candela. And from that I had derived dimensions for various quantities, velocity, acceleration, etc., mass transfer quantities, concentration, mass flux, diffusion coefficient, heat transfer quantities, specific heat, heat flux, thermal conductivity, momentum transfer quantities, stress, viscosity, surface tension, elasticity, etc. And I told you how to get dimensions of an unknown quantity based upon dimensions of known quantities and a relation that involves these unknown and known quantities. We had done that for a power law fluid, and we had also done that for electrical quantities, charge, voltage, resistance, capacitance, etc., inductance and so on. And I derived the dimensions of all of these quantities in terms of the fundamental dimensions. Note that all of these quantities involve only 5 dimensions: mass, length, time, temperature and current. Even though the quantities are very large in number, they involve only 5 dimensions. And I had also told you that equations have dimension. Each additive term in the equation has to have the same dimension. That is required for consistency, because if they do not have the same dimension, and if I change one dimension, let us say from meters to centimeters, and not all quantities contain this length dimension, then some quantities will change and others will not. The only way that the equation will be valid independent of the units used is if all quantities have the same dimension. I told you that derivatives have dimension. It's the derivative with respect to a quantity has dimension of 1 over that quantity, inverse of that quantity. Integrals have dimension. The integral of a quantity is proportional to the dimension of that, is equal to the dimension of that quantity as well. And I showed you that that relationship with respect to this Navier-Stokes equations as well as the momentum equation as well as the Bernoulli equation. This inverted triangle, which is the gradient operator, has dimensions of inverse length. Time derivative has dimensions of inverse time. So, now we will start dimensional analysis. When we are solving any problem, the objective is to determine some unknown quantity. I will call that the dependent quantity in terms of some other known quantities which are called the independent quantities. The known quantities or the independent quantities are what are specified. The unknown quantity, the dependent quantity, is what we want to determine. So, typically in any problem we will have one unknown or dependent quantity, dependent variable, as a function of a set of known quantities, known parameters or known variables. So, rather than writing the expression between the dependent and independent quantities in terms of dimensional variables, it is more compact to write it in terms of what are called dimensionless groups. The fundamental principle for this is what is called the Buckingham Pi theorem. And this states that if there are n dimensional quantities and m fundamental dimension. Okay. The problem can be equivalently expressed in terms of n minus m dimensionless groups. Okay. If there are n dimensional quantities, okay, if there are n dimensional quantities and all of these n dimensional quantities together contain m fundamental dimensions, mass, length, time, temperature, current, then I can write the problem in terms of n minus m dimensionless groups. So, I do not have to vary all n quantities, okay. I can get it equivalently in terms of n minus m dimensionless groups. There is of course subjectivity in how you define these dimensionless groups. Okay. As I said, for n dimensional quantities there will be one dependent dimensional quantity and n minus 1 independent dimensional quantities or independent parameters. So, you will get one dependent dimensionless group that you want to calculate and n minus m minus 1 independent dimensionless groups. Okay. So, let us look at a concrete example, okay, in order to illustrate this. Okay. Consider a sphere settling with a velocity v in some tank of fluid. Okay. The sphere has diameter d, okay, and the fluid has viscosity rho and density mu. I am sorry, density rho and viscosity mu. Okay. And let us assume that the linear dimension of this tank is L, say. Okay. The mass balance for the sphere, Newton's law, okay, I am sorry, the momentum balance for the sphere, Newton's law, is mass times acceleration is equal to the sum of forces. Okay. The gravitational force, which is mg, minus the force due to buoyancy. Okay. Gravitational force acts downward if gravity is in this direction. Buoyancy acts opposite to gravity. And there is another force called the drag force, which also acts opposite to gravity. Okay. The reason for the drag force is that as the sphere is moving through the fluid, there is a fluid velocity that is created around the sphere. Okay. As the sphere is moving through the fluid, there is the flow of fluid, okay, past the sphere. Okay. So, as sphere goes, there is fluid flow that is happening, okay, around the sphere, because in front of the sphere the fluid has to be pushed out and it has to come back on the rear side, okay, that generates a fluid flow. And whenever there is a fluid flow, there is frictional forces due to the viscosity of the fluid, and that causes a drag force. So, the drag force depends upon the properties of the fluid as well as the flow that is created, okay. And the flow that is created will depend upon the diameter of the sphere, the velocity of the sphere. Okay. For a given diameter and a velocity, you will get one particular flow field. Now, what are the dimensional quantities that affect the velocity of the sphere? Okay. For simplicity, for the present, I will consider that the length of this tank is very large, so that this L is not a parameter. Okay. If the length of the tank is sufficiently larger than the sphere diameter, this length will not be a parameter, and the only parameters that affect the drag force, okay, the independent parameters, which affect the drag force. The first one is the diameter of the sphere, d with dimensional length, the velocity v with dimensional length per unit time. Okay. I said that the drag force is due to the fluid flow generated by the motion of the sphere in the fluid. Okay. So, it has to depend upon the diameter and the velocity of the fluid. Okay. As the velocity changes, the fluid flow will change and the drag force will change. The diameter changes also, there will be a change in the fluid flow. Okay. There are also the viscosity and the density, rho with dimensions m L power minus 3, and there is the viscosity mu with dimensions m L inverse T inverse. Okay. So, these are the independent dimensionless groups, okay. And the dependent dimensionless group is the force, drag force F d with dimension m L inverse T power minus m, my apologies, this should be mass times acceleration m L T power minus 2. Okay. So, that is the dependent quantity. Now, I have to get independent dimensionless groups and dependent dimensionless groups. Okay. Independent dimensionless groups, I have to non-dimensionalize the force by some combination of density, viscosity, velocity and diameter. Okay. You can see that out of these, the density and the viscosity contains the mass dimension. So, the mass dimension, the drag force can be divided by the mass dimension in either of these two. Okay. Either choice is acceptable. Okay. I will first do the calculation by considering the viscosity, the diameter and the velocity for dimensional analysis to define a dimensionless drag force. This dimensionless drag force is scaled by viscous scales. Therefore, I will write this as F d v star, okay. Star denoting it as dimensionless and V subscript for non-dimensionalizing by viscous scales. Okay. So, this is the drag force times some combination of the viscosity per alpha, velocity per beta and the diameter per gamma. Okay. And these alpha, beta, gamma I have to determine from dimensional consistency of this relationship. The dimension on the left, drag force, dimensionless drag force is dimensionless. So, this is m power 0, L power 0, T power 0, this is dimensionless. Okay. We are getting a dimensionless drag force. The dimensional drag force has dimension of m L T power minus 2, okay. That is the dimensional drag force times the viscosity per alpha m L inverse T inverse per alpha, velocity per beta L T inverse per beta and length, the diameter per gamma, which is L per gamma. Okay. So, if I look at the individual dimensions, the mass dimension, okay, left side the exponent is 0, the right side the exponent is 1 plus alpha. Okay. Length dimension, left side is 0, right side is 1 minus alpha plus beta plus gamma. Okay. And the time dimension, left side is 0, right side is minus 2 minus alpha minus beta. Okay. This first one will give you alpha is equal to minus 1. Okay. Substitute alpha equal to minus 1 in the last time dimension and you will get beta is equal to minus 1. Okay. Substitute that into the dimension for length and you will get gamma is equal to minus 1. Okay. Therefore, the force scaled by viscous scale is the drag force by mu v d. That is the dependent dimensionless group. Okay. That is the dependent dimensionless group. Okay. So, in this problem, recall that I had 4 independent dimensional parameters and 1 dependent. These involve 3 dimensions: mass, length and time. Okay, these involve 3 dimensions: mass, length and time. Therefore, I should have 1 independent parameter and 1 dependent. Okay. Total 5 quantities, 3 dimensions, 2 dimensionless groups, 1 is independent, the other is dependent. Okay. What is the independent dimensionless group? Okay. This has to have some combination of the parameters density, viscosity, diameter and velocity. Okay. These has to have some combination of density, viscosity, diameter and velocity. Okay. I will use the notation Re for this. In this dimensionless group, there are 4 parameters. I can set any one parameter to the exponent 1 without loss of generality, because any dimensionless group raised to any power is still dimensionless. Okay. So, one of those exponents can be chosen as 1 without loss of generality. I will choose the exponent of the density as 1, okay. Then velocity per alpha, diameter per beta and viscosity per gamma. Okay. So, that is my dimensionless group. Okay. So, left side is dimensionless, m power 0, l power 0, t power 0. The right side m l power minus 3, velocity L t inverse per alpha, diameter L per beta and m L inverse t inverse per gamma, okay, from this relationship. Okay. And if I take the exponents of each of these, okay, the exponent of m, I get 1 plus gamma equal to 0. Okay. Exponent of the length dimension, okay, I get minus 3 plus alpha plus beta minus gamma equal to 0. Okay. And the exponent of the time dimension, okay, I will get minus alpha minus gamma equal to 0. From this relation, I will get gamma is equal to minus 1, okay, because 1 plus gamma is equal to 0, gamma is equal to minus 1, minus alpha minus gamma equal to 0. Okay. So, minus alpha plus 1 is equal to 0, okay, which gives me that alpha is equal to plus 1. Okay. And I substitute that into this expression for length, gamma is minus 1 and alpha is plus 1, and I will get beta is also equal to plus 1. Okay. Therefore, the dimensionless group, okay, gamma is equal to minus 1, alpha and beta are both plus 1. The dimensionless group is the what is called the Reynolds number, rho v d by mu. Okay. So, therefore, my relationship between the drag force and these different parameters. Okay. So, in this particular case, the drag force was equal to some function of rho v d and mu. Okay. That was the original relationship. The drag force was dependent upon the diameter and the velocity of the particle, as well as the fluid properties, the density and the viscosity of the fluid. Okay. So, by dimensional analysis, I have reduced it to a relationship between just 2 quantities, f dv star is equal to some function, okay, So, whereas my original expression had 5 quantities, 1 dependent and 4 independent, using dimensional analysis I have reduced it to just 2 quantities, 2 dimensionless groups, 1 dependent and 1 independent. Okay. So, that is the big advantage of using dimensional analysis. You can significantly reduce the complexity in a problem by expressing it only in terms of dimensionless groups. In this case now, in order to find out the drag force, I know it is only a function of Reynolds number, that combination of density, viscosity, diameter and velocity. Therefore, I have to do experiments only by varying one parameter, whereas if I did not use dimensional analysis, I would have to independently vary the density, the viscosity, the diameter and the velocity and so on to get the final expression. So, in this particular case I had scaled the drag force by viscous effects. When the Reynolds number goes to 0, if it becomes very small, right, the function of this Reynolds number, okay, it has to necessarily tend to some constant value, okay, because when the Reynolds number becomes very small, okay, when the Reynolds number becomes very small, it means that the density is no longer a parameter. Okay. When the Reynolds number becomes very small, it means that the density is no longer a parameter. So, now you have only 3 independent parameters: viscosity, velocity and diameter. And when you have only 3 independent and 1 dependent parameter, that means that for the Reynolds number much smaller than 1, this f dv has to be equal to a constant. Okay. So, dimensional analysis tells you that the drag force has to the scaled drag force has to depend upon the Reynolds number. In the limit of the Reynolds number becoming small, it tells you that the scaled drag force has to go to a constant value. It does not tell you what that constant value is. For that you actually have to solve the problem, okay. And if you actually solve the problem, you get what is called Stokes drag law, okay. This constant turns out to be equal to 3 pi for 0 Reynolds number, but up to that constant value you have got the dependence of the drag force on the parameters just by dimensional analysis. The drag force is some function of the Reynolds number. In the limit as the Reynolds number goes to 0, it goes to a constant. We do not know what that constant is, but that we can find out by experimentation. At the beginning I told you that I will scale the drag force by the viscosity. We had a choice of 2, density and viscosity, and we chose to scale it by viscosity. That is appropriate when effects of density or effects of inertia are small, and inertia is small when the Reynolds number is small. The numerator in the Reynolds number is represents inertial effects, and the denominator represents viscous effects. Okay. So, when the Reynolds number is small, inertial effects are small compared to viscous effects. Viscous effects are dominant, they have the dominant contribution to the drag force, and therefore, I can scale the force by viscous effects. When in the opposite limit, when the Reynolds number is large, okay, viscosity is not important, and therefore, one has to scale the drag force by the density. Okay. Okay. And you can do that calculation, okay, f d I. Okay. It should be drag force rho power alpha v power beta d power gamma. Okay. And you go through the calculation the same way that we had gone through the calculation earlier for the viscous scaling. Okay. And you will find that this correction is f t by rho v square d square. Okay. Rho v square d square you can verify has dimensions of mass, length, t power minus 2. Okay. So, this is this drag force scaled by inertial scales, which is appropriate for high Reynolds number where inertia is dominant. F dV star is the drag force related by viscous scales, where viscous forces are dominant. Okay. And you can easily verify that these two are related. Okay. F dV star into R E inverse, okay, gives me the inertial scale. Okay. So, if I just take F dV star is equal to F d by mu dV, okay, and if I take 1 over R E times F dV star will be equal to F d by mu dV into 1 over R E is mu by rho V d, okay, and this viscosity will cancel out, and I will just get F d by rho V square d square. Okay. So, therefore, you would scale it by viscous scales when viscosity is large or the Reynolds number is small. Viscous effects are large. You would scale it by inertial scales when inertial effects are large and the Reynolds number is high. Okay. The dimensionless group that is actually used, okay, for this drag force, okay, is what is called the drag coefficient. Okay. The drag coefficient C d is defined as the force per unit area perpendicular. Okay. C d is defined as a pressure divided by a kinetic energy per unit volume. Okay. Pressure has dimension m L inverse T power minus 2, you recall. Okay, that is the dimension of pressure. Energy, so pressure is a force per unit area, mass length T power minus 2 divided by L square. Energy has dimensions of mass length square T power minus 2, okay, force into distance. Okay. So, energy per volume is equal to m L square T power minus 2 by L cubed, which is m L inverse T power minus 2. Okay. So, an energy per unit volume has the same dimension as pressure. Okay. So, C d is defined as a pressure, okay. Pressure which is the drag force divided by the projected area, area projected perpendicular to the flow, pi d square by 4, divided by a kinetic energy per unit volume, that is half rho v square. Kinetic energy is half m v square, kinetic energy per unit volume is half rho v square. Okay. Okay. So, this is equal to F d by rho v square d square, okay, into I have a 1 over 4 here, okay, I have 1 over 2 and I have a pi. So, this will be 8 by pi, okay, which is the inertial pressure into 8 by pi. Okay. So, within a constant factor, into 8 divided by pi. So, within this constant factor of 8 by pi, the drag coefficient is the same as the drag force scaled by inertial effects. Okay. So, in this class I had explained to you the drag force calculation based upon the diameter, velocity, the density and the viscosity of the fluid. How do we calculate the drag force? How do we non-dimensionalize the drag force? There were initially 4 independent and 1 dependent dimensional quantities. Using dimensional analysis, we had reduced it to just 1 independent and 1 dependent dimensionless groups. We were able to further simplify it in the limit where the dimensionless group, the Reynolds number, was small or large. Reynolds number represents ratio of inertial and viscous effects. When it is small, viscous effects are dominant and the drag force scaled by viscous scales has to be a constant. When it is large, the drag force scaled by inertial scale has to tend to a constant value. If viscous effects are small compared to inertial effects. So, I will continue this discussion of dimensional analysis for the flow past objects in the next lecture. I will briefly summarize the Buckingham Pi theorem before I go on to other problems involving dimensional analysis. I will continue this in the next lecture. I will see you then.